So, so this is a quick overview of things that we'll be talking about. So the question is, what is friction? You should know that this friction here is a form of a force, and it tends to oppose the motion of the body. So for you to have friction in action, there must be two surfaces in contact. So let's see what is on the slide here. So when the body slide or tends to slide on a surface on which it is resisting, a resisting force opposing the motion is produced at the contact surface. So this resisting force is what we call the friction force or frictional force. So remember I mentioned that it's a form of a force. Okay. And you must note that friction always works in the direction opposite from the direction the object is moving or trying to move. And it always slows the moving object down. Can we still hear me?
Yes, sir.
Okay. So which implies that if you have the applying force, for example, let's say one of you is applying the force to this block here. Of course, the object is meant to move in the direction of the force. So let's say it is moving forward along the positive x-axis. The presence of frictional force is going to make like it's going to be resisting.
Avad.
Who is that?
Avad, you mean?
Ryan, mute yourself. Okay. So if there is a force applied that is pushing this block in the positive x-axis, there will be a resisting force, a force that tends to oppose the motion of that object. That force that tends to oppose that motion and always in the opposite direction is what we refer to as the frictional force, which is F of F, as you can see here. So aside from these two forces, the applied force and the frictional force, there are other two forces that are acting on that object. There's the one acting vertically upwards, that's in the positive y-axis, that's the normal force, that's the normal force of the body. And then there's a force that tends to go down, vertically downward, acting vertically downward on that object. That is the force due to gravity, which is F of G. So you need to be quite familiar with diagrams like this so you can know which is which and also how to apply them to solving of questions. All right, so you see this friction here can be limiting. So if contact surface is smooth, frictional force will be less. However, if the contact surface is rough, you expect the friction force to be more. So I'm going to say that for a perfectly smooth surface, you expect friction there to be zero. Are we together?
Yes, sir.
Yes, sir.
Okay.
Sir.
What do I mean by perfectly smooth surface? For example, someone walking on like if you look at all these icy regions that are very cold, uh regions that are very cold. For example, their water bodies would have almost everything would have turned to ice. So in that kind of surface, you can't work on it. You just keep falling. So let's say maybe one big iceberg or something. So those kind of surfaces, the frictional force on those surface is zero. That is, it is not like it cannot support uh it is zero to the point that it can't even support working. So expect that the frictional force on a perfectly smooth surface to be zero. So limiting friction. Limiting friction is what you call the maximum friction force that can be developed at the contact surface. So when body just on the point of moving is called. Oh wait, sorry. Um. Okay. Let me say that it is the maximum frictional force that can be developed at the contact surface when a body is just at the point of moving. So when a body is just at the point of moving, for example, let's say you're trying to push a table you're trying to push a table in a classroom. Of course, the you exert a force if there are three conditions there. If we are trying to push a table from on a that is on a ground surface, number one is that the force that you are applying may either be less than the force that is opposing it. Okay, let's try to write that on a whiteboard. Okay, so suppose you have something like this. Okay, and then you have this to be, let's say, a table in a classroom. This is the table. You are here applying a force. Now, you are applying a force F, trying to pull the body in that direction. In that direction. Now, normally you expect the frictional force to act in the opposite direction. So this is my frictional force. I'll be using FR in this case. So there are three possible conditions. Three possible conditions, okay? So number one, you can have F is less than this FR. Number two, you can have F is equals to FR. And number three, you can have F is greater than FR. So in which of these conditions do you think the object would move? Who can tell me? Am I
Three.
okay? That is three, right?
It is.
In which of these conditions do you expect the body just about to move?
Lisa.
Two. Very good. And in which of the conditions do you expect the body or the object not to move at all?
That's one. One.
Okay, that is one. So here, okay, let me write what each of those stuff mean there. Okay, this is condition there. So this F is what you call the applied force, and this FR is what you call that frictional force. Okay, that's the frictional force. So in this place now, you expect no movement. Okay, here you expect just about to move. Just about to move, and then here you expect move definitely. Okay, so it is in this condition too that you have the case of a limiting friction when the object is just about to move, when it's just about to slide. That is where you have a limiting what? A case of a limiting friction. Okay, so that is what I want to explain there. So let's continue the presentation quickly. So uh now what are the types of friction that we have? Quickly, we have two kinds of friction. You have the static and then you have the dynamic friction. Static, dynamic. And the dynamic is further divided into the sliding friction and the rolling friction. Sliding and rolling. Okay. All right. So each of them here, if they ask you that in which condition or in which type of friction do you expect the frictional force to be more? So you expect frictional force on it, like in this static friction, to be more than what you have in dynamic friction. Okay. So in static, the force, the object hasn't begun motion at all. There hasn't been any motion started at all. That is static. That is probably okay. For example, you have in a classroom, you have a chair, a table on a ground surface. So when you go there and you try to push the table, that kind of friction that is experienced between the surface, between the point of contact of the table and the ground surface is what you call the static friction. Why? Because the object hasn't begun motion at all. Okay, it's just about to move. That's when your force, when the the force you're applying is equal to the frictional force. So those kind of friction I explained just now is called static friction. Now, in the case of dynamic, the body has already begun motion. Motion had started already. Motion had started already. So even though motion had started, there's still some kind of friction that is trying to oppose the motion of those two surfaces in contact. Remember, I mentioned that for friction to happen, there must be contact. And that contact must be between two surfaces. So in the case of dynamic friction now, probably you have which example should I use there? Uh, okay. For example, look at the wheel of the car when it's on motion. Yes, the wheel of the car is already moving, and also on the ground surface as well. There's a kind of relative motion between the two of them while the car is on motion. So that kind of friction that you expect to see there would be a dynamic friction, not static. But at the point whereby you just started the car and it's just about to move, that would be static. But when the motion had started already between the car and between the wheels, that is the car tires, and the ground surface, you expect dynamic friction there. Now there's now sliding friction and rolling friction. So between sliding and rolling now, the one that is more, you expect sliding friction to be more than rolling friction. Are you all understanding what I'm trying to say?
Yes, sir.
Yes, sir.
Okay. So which means that you expect you expect what's it called now? Sliding friction. Okay, sorry. You expect that sliding friction is greater than dynamic friction. Okay, so that is f of x greater than f of k. Okay, f of x is greater than f of k. So this f of x is this one, that's sliding friction. Oh, sorry, I mean not sliding. Sorry, I mean static here. So I mean static there. So f of static is greater than f of dynamic. So, and remember that this dynamic friction, who is that disturbing us, is divided to sliding friction, who is that? Then we have rolling friction. So between these two now, let's suppose this one is f of SL, that's sliding, and this one is f of R. So you expect f of SL to be greater than f of R. That's rolling now. Rolling, sliding. So that is what the slide is trying to tell you. So let's continue quickly. Now, there are some angles that you need to know as far as friction is concerned. Um, okay, before talking about this one, you need to know some basic laws of solid friction. Okay, so aside from before moving into the angles that we need to talk about, so you need to know laws of we do call it laws of solid friction anyway. So number one thing there that you need to know is that the law, one of the laws or the first law came directly from the definition for friction. Number one, you are going to say number one, it's opposite motion. That will be number one for law of solid friction. Number two, it's it acts, you must know that it acts between two surfaces in contact. Between two surfaces in contact. And then number three, you should know that it is dependent. It is dependent on the nature, now, nature of the surfaces in contact. So what are the nature? E.g., a surface may be dry, a surface may be wet, a surface may be painted, a surface may be smooth, a smooth surface may be rough. Okay, etc. Number four, you know that the force of friction now, force of friction is directly there. That is directly proportional. Is directly proportional to the normal reaction force. Okay. And then the fifth one is that it is independent. It is independent. It is independent of the surface area. Or let me say, it is independent of the area of the surfaces in contact. So these are the laws of solid friction, and you must be familiar with them. Number one, I said opposite motion. Number two, act between two surfaces in contact. Number three, it is dependent on the nature of the surfaces in contact, e.g., whether a surface is dry, wet, painted, smooth, rough, etc. And also the force of friction is directly proportional to the normal reaction force. And then it is independent of the area of the surfaces in contact. So let us have a diagram quickly. I hope you get that.
Yes, sir.
Okay. No, that is a bad one. Let's have something like this. Oh, that's too somehow. Okay. Do I remember how to write on this thing? Right? Not sure if I do. It's actually writing. Oh, it is. Okay, anyways. I don't know how come everything is so thin. Alright, that's okay then. So suppose you have goodness. You have this object here. Now let's say this is the center point here. There are some forces. Okay, you apply a force along this direction. There's a force applied there. Let me zoom it in so that we can see it properly. Okay, but I don't know why everything is so thin. Let's see if I can increase that value. Okay. Then this go that way. Remember, we already mentioned that if this is a force applied, if that's the direction of the force applied, that is, it's pushing it this way, it's pushing it that way, the frictional force is going to go in the opposite direction, FR. There's a normal force that goes up, normal force that go up, that is normal reaction force, R. And there's a force acting downward. That force acting downward is the weight, okay? So it has been obtained. Okay, this weight is equals to mg, right? And this reaction force, when you take the algebraic sum of forces acting along the vertical axis, summation f of y will be equal to 0 because there is no acceleration going along that vertical axis. What I'm trying to do here is that normal f is equals to ma according to the Newton, according to Newton's law. Whatever the force that is acting in the body, the algebraic effect or the resultant of it must be equal to ma. But since, okay, let me do it this way so that you don't get confused. Normally, the resultant force along the vertical axis, that's f of y, is equals to mass and product of, okay, product of mass and acceleration along that y axis. But since there's no motion along that y axis, a of y is equals to 0. Since no motion along y axis, yes, you are pushing it along horizontal axis. You don't expect it to be flying up and down. So that's why acceleration along y is 0. So which means that at the end of the day, you're going to have the algebraic sum along this y equals to 0. By the time you multiply 0 with mass, everything tends to be 0. So what is that equivalent? It means that this reaction force here, this one lies in positive y-axis, and this one lies in negative y-axis. Right? Are you guys following?
Yes, sir.
Yes, sir.
Okay, so if that is the
Yes,
case,
sir.
you need to get the resultant. You're going to take the positive minus the negative. So that algebraic sum is now R minus W equals to 0. So you have R is equals to W. W is equals to what? Weight, which is equals to mass times acceleration due to gravity, G. So that is how we obtain that the normal reaction force is exactly equals to the weight. So that is equals to mass times acceleration due to gravity. That is vertically. Now, horizontally, there are two forces there. This is force F, which is the force we are applying, and there's the force in the opposite direction, F of R, which is going negative x axis. This one is going in positive x axis. So because there's a remember that your the motion will always be in the direction of the force. So you expect the acceleration to go that way. You expect it to go this towards right direction. That's positive x axis, right? So if you want to get your resultant along the x axis, we say the algebraic sum of the forces along x must be equals to ma along x. So that that's acceleration along the x axis. Are we together?
Yes, sir.
Yes, sir.
Okay. So that's mass times acceleration along the x-axis. Now, because there's acceleration value along the x-axis, you don't expect this guy to be zero, to not be zero. Now, the resultant of this force, that will be the one in the positive, F, minus the one on the negative x-axis, FR. So which means that you're going to have F as the force applied minus FR is equals to MA. F minus FR is equals to MA. So please note that this will be the is that going to be transparent? Going to be uh, no, I didn't need that. Okay. So do note that this equation is very, very important to know as far as friction is concerned. It's the formula that you need to know. Suppose you are given a question, you have your frictional force, you have your mass, you have your acceleration, and then you are asked to calculate for the force that is applied or force that tends to cause the motion. That means you want to solve for F. So please note this formula down somewhere. Okay. Now it is important that um sorry, it is important to note that in the case of limiting, in the case of limiting friction, in case of limiting friction, what do you expect? The object is just about to move. In the case of limiting friction, the object is just about to move. Just about to move. So if it's just about to move, let's refer back to this equation here. In the case of limiting friction, the object is just about to move. So if it's just about to move, that means that you expect acceleration along that x-axis, right? You expect it to be zero. Now I'm talking of in the case of limiting friction now. Now, if this acceleration along the x-axis is zero, everything on this side will be zero. So you are going to have F minus FR equals zero. And if that is the case, you're going to have that the force is equal to FR. Okay? Are we still together?
Yes, sir.
So,
Yes, sir.
so this is the case of limiting friction because the body is just about to move or is just about to slide. It hasn't accelerated, so acceleration is zero. So you have F minus F equals zero according to this equation here, this one, and then you're able to have that F equals to F bar. Now there's something important from that law of solid friction. Look at the number 4 of the law of solid friction. We say that the force of friction is directly proportional to the normal reaction force. What that one is telling you is that force of friction, F of R, is directly proportional to the normal reaction force. That is what it's telling you. So if that is directly proportional to that, So let's quickly work out something here. Um, if force of friction is that proportional to R, if you want to remove this proportionality sign, you're going to introduce a constant. So f of R can be equal to a constant. That is where you introduce coefficients of friction and then R. So this guy here, I call it coefficient of friction. Are we together?
Yes, sir.
So this guy here, we are going to call it coefficient of
Yes,
friction.
sir.
Okay, so which means that f of R can be equals to mu. We call it mu R. So that mu, you can come and put it here. So in the case of limiting friction, the force, or let me say in the case of limiting friction, the frictional force is exactly up to the force that tends to cause the motion. Or frictional force is exactly same as the force applied. So F equals to FR, which is equals to what? Mu mg. So I will stop there for the derivations of some important things that you need to know as far as friction is concerned. Is it clear to everybody?
Yes, sir. Yes, sir. Yes, sir.
Okay, thank you. So we continue quickly. So in angle of friction, we've already explained this one. So the friction, this is the force that tends to what's it called? Okay, sorry. This P, we are using P here as the force that want to is pulling the body this way. You must be able to differentiate pull from push. Push is you are exerting a force straight directly on that object. That is, you are pressing on it. And pull is that you are pulling away from it. So you have to hold on it and pull away. You have to hold on it, move away. But push, you have to hold on it and then move inward. So push from pull. So in this case now, this letter P is a what? Is it a force of pull or a force of push? You can tell me.
Also, cool.
Okay, so P is a force of pull. So if we are pulling in this direction, this is the frictional force in opposite direction. You can see in opposite direction to that. And then here you have some kind of angle of inclination here. So when you're having something like this, there's a way we solve it. Solution of this is that you're simply going to resolve the force vertically, and also you are going to resolve it horizontally. Look at the R there. The R is they are saying that the R, which is the one inclined there, is the resultant of N and F. Well, let me see. Okay, if R is just the resultant of N and F, then we don't need to be so much concerned about that. Reason being that R is not so different from this guy, F, and this guy, N. So at the end of the day, to still eventually lead us to, uh, what's the call now? It's going to lead us to what we just did here. Where's it? So that one is just trying to look for the relationship between this capital F and this R, which we do not actually necessarily need. As much as we have this F and we have this R, it is good. It will only be a different case when it is you are not giving this force here, but rather you are giving the force inclined this way. What I'm trying to say is that it will be a little bit different when you have something like this now. When you have something like this, you have this get here. Okay, okay. normal reaction force. In that one, you have your weight. So let's say maybe force of friction, and then you now have a force in this direction. Sorry, that is meant to be like F, and then it is inclined at an angle theta. So in this case now, what you are going to do, are you following?
Yes, sir.
Yes, sir.
Okay. So in this case now, what you are going to do will be that you must resolve this F to the to this vertical and to the horizontal. When you make reference back to this slide, it was stated that this area is a resultant of N, that's this one, and then F. This F is equivalent to the F that you have down here. Okay, so let's make reference back to this one. So which means that I must find the components of this guy along this R, and I must look for the components of this F along this direction. So what are we trying to say? Focus on the diagram very well. You are simply going to have something like this. Let me use this one if it's going to be very clear. Uh, okay, which will be same as this one going up here. Sorry that diagram is not completed there. So we are going to have, if this is F now, you have a kind of a complete triangle. This side that you are seeing going like this, if this is F of X, it is equivalent with this side that is going this way. Take a look at their direction. Let me use this one. Take a look at the direction again. You want to form a closed triangle here. If you represent this as F of X, it must be same as the F of X that you are having here. And if you want to resolve this F here to horizontal, or let me say to vertical, in this, when you flip the diagram over, or when you look at this triangle here, this is the opposite side. Like this angle, this is the angle, right? Angle theta. And usually the side facing the angle theta is the opposite. That means this side will be the adjacent, and this side will be the what? Hypotenuse. This will be hypotenuse. This will be opposite. This will be adjacent. So you want to resolve this force F into opposite and adjacent. That's F of X and as well F of Y. Are we still following?
Yes,
Yes,
sir.
sir.
Okay. So to resolve this F now into F of X, what are you going to do? What's relationship? That means you're having opposite and you're having what? Hypotenuse. So when you are having opposite and hypotenuse, once you remember, you want to use your SOHCAHTOA. So when you're having opposite and hypotenuse, this best fits in. So which means that you're going to say sin theta is equals to opposite, that's F of X that we want to solve for, and then hypotenuse, that's F. So it implies that F of X in that direction will be equals to what? F sin theta. So this F of X is equals to F sin theta. And then to get the adjacent side, which is F of Y, this means this is adjacent, and then this is hypotenuse, which is F. So you want to relate it to what? To car. What relates them together is car. So that means cosine of the angle is equals to adjacent, that's F of Y, over hypotenuse F. So that means F of Y is equals to F cos theta. So if that is so, this one is equals to F cos theta. So what now happened? Your diagram changed to something like this. Diagram changed to something like this. You know why that's usually okay. Diagram changed to something like this. So you're going to have your f of r in that direction, f of r. You are now going to have the f of x here, which is what? Which is f sine theta. Going up here, you are going to have two things. Sorry, I'm trying to make the diagram as thick as possible enough. That arrow rather. So there will be two things going up here. R and what? And f of y. Are you getting me? Which equals to f
Yes, sir.
cos theta. Are we still together?
Yes,
Yes, sir.
sir.
So your diagram changed to something like that. So that way, I've been able to resolve the forces into vertical and horizontal. This is your normal weight there, which is equals to mg. Okay. So you still go back to your normal what's it called now? The fact that the summation of the forces along vertical f of y was equals to zero. Why? There's no acceleration along the vertical axis. So at the end of the day, you're going to have what are the things you have on the positive y? That's r and f of y. You have r plus f of y minus the weight, which is what you have on the negative x-axis, w, equals to zero. So which means that you're going to have r plus f of y equals to w. So that means, okay, let's say r will be equals to w minus f of y. So which implies that this r equals to w. Remember that your f of y is equals to what? F cos theta. So you put it there minus the force cos theta. So that is that for that vertical. Now then for horizontal, horizontal is pretty straightforward. The summation f of x along our horizontal axis must be equals to m multiplied with acceleration along the horizontal. Now we are pulling with this force here. That's f sine theta. We must have f sine theta minus f of r to be equals to ma. Are we together?
Yes, sir.
Does it make sense? So in this regard now,
Yes, sir.
this will be your in this regard now, this will be like your equation one, and then this will be equation two. And then remember that f of y is equals to mu r. So further looking at it, you are still going to have f sine theta minus your mu r is equals to ma. It now depends whether they tell you that the object is just about to move. If it is just about to move, that means that your acceleration will be zero. And then this your r here, you can, your r, you have it as a representation here, w minus f cos theta. So it all depends on the question you are given. It's just the understanding of the concept that matters. So I hope you understand how we do this resolution, how we resolve from this down to this one. Does it make sense?
Yes, sir.
Okay. So quickly, I'll just move away from this one. You tend to appreciate it more when you want to use it to solve questions. Okay. So coefficients of friction, yes. Remember that we mentioned that limited friction is that proportional to normal reaction force. So F is that proportional to N, or if you use R. So if you take the ratio, that's F divided by N. So it has been obtained that what's it called? This F, let me see where we can derive that from here. Did we derive that here? Not here. Here. Okay, all these ones are not having any angle involved. Okay, let me just say for now, take it that coefficients of frictional force where you have angle of inclination involved. Okay, let's have it quickly here. Suppose you have this inclined plane. It's an inclined plane. There is angle theta here, and you have a mass directly on the plane. You must be very familiar with an inclined plane in the sense that when you have objects like this, there is normal reaction acting upward, normal reaction force, that is R. There is this equivalence of that. There is a weight, the weight of the object acting downward. This is the weight here, which is equal to mg. Here, there is a resolution of this weight at this point here. That one is mg cos theta. And then there's a weight component acting downward. That one is mg sin theta. So it is on this inclined plane you can have coefficients of friction equals tan theta. Why? Because coefficient of friction is equals to ratio of the what's it called now? Of the friction and the normal reaction force. So you should try to prove this yourself. That's given as an assignment. Try to show that on an inclined plane with an angle theta involved, that the coefficient of friction is equal to tan theta. So you need to check that out. So continuing from where we stopped, let's move further. So that angle of repose, this is the angle of repose we are talking about. That is alpha. So with increase in angle of the inclined surface, the maximum angle at which body starts sliding is called the angle of repose. You know, inclined plane. Suppose this line here, this one that's moved up, this hypotenuse side. Suppose it is lying flat like this, and then we started increasing it small, 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 up to the point that the mass on it then starts to slide down. At that point, that angle that is measured here is what you call the angle of repose. What I explained now, does it make sense?
Yes, sir.
Yes, sir. Can you explain it?
Let me explain it again. Let's say that this hypotenuse line here, assume that it is just lying down. Okay, let me use a whiteboard to explain it. This is the normal horizontal line. Now let's say that you have the other line lying on that same thing here, and then you have the mass like this. Now we are now raising this line, we are raising it up gradually. The first one, we have something like this. The second one, we continue to raise up. The second one, we have something like this. And then the third one, we have something like this. The angle at which this thing has started to move downwards, that angle measured there is called the angle of repose. Do you understand now? Which means that as at this
Yes, sir.
which means that as at this point, it has not started sliding. It has not started sliding here. But here now it has started sliding down. So that angle is what you call the angle of repose. So it is what you call the angle of repose. So, and remember I've shown you that the resolved components of this the weight is the one acting this way. So along this line is the resolved component of the weight in this direction. The angle alpha is equivalent to what we have here. This is still alpha, and this is that's another alpha. So this one will be W cos alpha, and this one will be W sin alpha. So I explained that here. So this one acting here is mg cos theta. This weight here is mg. So this one acting straight down is mg cos theta, and the equivalent one, the one that will be here, which will be acting this way, that's mg sin theta, and that mg sin theta, this is it here. It is equivalent to what you are having here as well. So this is the mg sin theta here. This is the mg cos theta acting down here. So this mg sin theta, what we call it is, we call it weight component down the plane. This one, what we call it, we call it weight component along or across the plane. So let me say that this one will be weight component down or parallel. Weight component down or parallel to the plane. Can you see that? And this one is weight component along or across the plane. So you must be able to distinguish weight component down or parallel and the weight component along or across. Does it make sense?
Yes, sir.
Okay, so I told you to check how do we obtain coefficients of friction mu to be equals to tan theta or tan alpha, whichever representation you are using for your angle. So try to take that as an assignment and try to figure that out. Also, still mu equals to tan theta or tan alpha. So, anyways, this is not so important here. So this is the case of bladder. I'm not sure if bladder is something you need to know. However, we can discuss it. So when you have bladder against a wall, so this is wall here and this is floor. So there are some forces that are acting from the floor against the ladder and also from the wall against the ladder. So you always remember that a ladder is always inclined. It's always inclined at an angle. So it's not just, the person cannot just put it straight. It must be inclined because there are some reactional forces. There are some reaction forces that come from the ground surface and also from the wall surface. So that is one there as well. I don't think you have ladder questions in your whole level. And then wedge, well, not very important. Screw traction fraction. Well, these are all what's it called now? Applications of frictional forces. Friction basically. So that will be the end of that presentation. Do we have any question or questions? Oh, really?